Welcome, and thank you for joining us for this webinar presentation. We are the Defense Systems Information Analysis Center, or DSIAC, one of 3 IAC domains in the DoD Information Analysis Centers operating under the Defense Technical Information Center, DTIC, within the Office of the Undersecretary of Defense for Research and Engineering. Our informative webinar series highlights current and emerging research and technology developments. It presents an opportunity for accelerating the DoD's leverage of these advancements by increasing awareness and fostering technical collaboration. DSIAC serves as one of the premier information research partners and curators of technology advancements and trends for the defense systems community. As such, our organization supports those working in the defense systems domain of DoD research and engineering. We do so by helping navigate the vast landscape of scientific and technical information, allowing our customers to get a head start on their technical projects. With an understanding of the defense system's DoD research and engineering landscape, we provide research and analysis services. We help unlock access to information, knowledge, and best practices from government, industry, and academia to stimulate innovation, foster collaboration, and eliminate redundancy. We hope you enjoy this webinar presentation and that it serves as a catalyst for community collaboration and improved DoD defense systems research.
Well, good morning, afternoon, evening, wherever you are. Thank you for joining us. My name is Brian Benish with DSIAC. Hopefully you were able to see that video and hear some of the clips from that video. That's just our quick introduction to who we are and what we do, and hopefully give you some context for why we offer these webinar series. Thankful today for Dr. Chung to have the time to present on the work they're doing over at DARPA. And so he's going to be bringing up a screen share as I just give a quick introduction to this webinar platform, so everyone's ready for that. This webinar platform, Any Meeting, is set up so you can ask questions during the presentation. They will go into a queue, and at the end of the presentation, we'll do a little bit of a Q&A. So at any time during the presentation, if you do have a question you'd like to ask Dr. Chung, there's a View Audience Questions icon at the top middle of your screen. You can click that, enter your question, and submit it. I want to distinguish that from the chat, though. There is a chat where you can chat with the presenter and other folks. I would ask if you do have a question to instead put it in the question queue and not the chat, so you can differentiate those. Beyond that, the just basic format here, Dr. Chung will have the floor and deliver his presentation, and then I'll chime back in at that point and help moderate a little bit of Q&A, and then we will go from there. So I don't want to take up any more time for Dr. Chung, so I will go ahead and hand the mic, so to speak, over to you for the rest of the time.
Great, Brian, thank you so much. Just want to do a comms check. Can you hear me?
Yep, you were coming in good.
All right, awesome. Well, thank you everyone for dialing in for this webinar. It's a pleasure to join you this afternoon, morning, or evening, wherever you may be. As Brian mentioned, my name is Tim Chung. I'm a program manager at DARPA, that's the Defense Advanced Research Projects Agency, and my home office is here in the Tactical Technology office. And so what I'd like to do today is share a little bit about some of the programs that we have been going on at DARPA that I've had the privilege of being the PM, the program manager for. One in particular is that I'd like to share is focused on accelerating innovations in complex environments. And so this offset program, otherwise known as the Offensive Swarm-Enabled Tactics program, it really is designed to help push and discover where innovative technologies might lie for enabling large-scale teams of air and ground robots in order to support small unit forces operating in complex urban environments. So if I may, I'm going to pull that apart a little bit and highlight the key elements where we're interested in discovering these types of innovative technologies. In particular, the large-scale teams of air and ground robots, we're talking about hundreds of drones and rovers, anywhere from 250 robots, 200 to 250 robots in these types of environments. We're talking nominally 8 square city blocks, so about a square mile, conducting operations over, let's say half a day. And the reason for this idea of air and ground is understanding the role of heterogeneous teams of robots going out there and operating and executing missions of interest to a commander. The small unit forces, this is really teasing out the fact that I didn't want 250 soldiers or Marines running around with joysticks, heads down, trying to operate these robots. But in fact, if we were trying to support something like a company level operation, how would we consolidate the orchestration of the swarm's actions to maybe one, at most two persons, swarm commanders, as we like to call them, in support of these small unit operations? And then finally, the complex urban environments, just due to the nature of the 3D structure, the limited maneuver and mobility, the visibility being limited due to occlusions, verticality being a key attribute of these urban environments. How can possibly swarms of air and ground robots be used in those urban settings? And so the offset program really is interested in trying to tease out the technologies associated with supporting such a vision and highlighting that there are many technologies that need to come together to fully realize the swarm capabilities here. Offset's carving out two key areas, enabling technology areas of swarm autonomy. How do we get teams of robots to work among and within themselves as a group? And then the second pillar is the human swarm teaming. How does human swarm commanders or operators interact and partner, truly team with these swarms of robots? And we recognize there are a slew of other technologies that are absolutely required in the area of logistics, swarm networking, and swarm perception to fully realize this vision. But we're starting with these two building blocks of swarm autonomy and human swarm teaming. And so we have structured this program to go through the development cycle in the context of minimum viable missions. We've broken that up into 3 vignettes, straight from the warfighting pubs for how to conduct military operations in urban terrains. And so phase 1 of this program focused on isolating an urban objective, smaller scale, smaller team, really focusing on an ISR, kind of a surveillance and intelligence collection type of a mission. So how do we disperse robots to go off and do that in a short amount of time? Phase 2 of the program looked at now expanding the scope a bit, not only doing that aerial surveillance or ground-based surveillance and reconnaissance, but also now needing to maneuver indoors to conduct an urban raid. How do we position forces around, above, and also inside buildings in an urban setting to conduct this particular type of urban mission? And then finally, the idea of bringing all of that together. These are missions that build upon one another, culminating in seizing key urban terrain. This is where we would seize and defend and hold swaths of an urban environment, maintain continuous awareness of the surroundings. But now we're doing this over longer periods of time, larger areas with a significantly larger swarm size as well. And so through this iteration, kind of in a MVM, minimum viable mission construct, we're able to continually build as the technology itself was evolving. Kind of coupled with that, I'm a roboticist by training. I love building and breaking robots, and that's where we tend to find and learn the most. And so in accordance with that philosophy, the experimentation campaign that we conducted throughout this program was focused on going out nearly every 6 months and really pushing the performers, the contractors developing these technologies, to demonstrate some elements of these capabilities in an iterative fashion, time and time again, every 6 months at a new test range across the country. And so as you can see here, we went from FX1 all the way through FX6. We hopscotched around the nation to a variety of different urban training facilities and test sites. And this was in part, of course, so that we can ensure we're not overfitting our solution to a given test range, but rather emphasizing that the solution space needs to be adaptable to a new venue, and also for our government team, in fact, to also keep it on its toes, so that instrumenting and equipping a test site for autonomy test and evaluation and assessment was also something that we could continually refine in hand in hand with the technology development. And so I'll just call out here that we recently concluded the CULX, the culminating experiment at Fort Campbell, a couple months ago. We did have to cancel FX5 due to COVID, but we're able to ramp back up pretty quickly to conduct this final experiment at the Cassidy Cactus, located in Kentucky and Tennessee. And so I'll share a little bit more about that throughout this talk. So in particular, I'll show you some footage from the Fort Campbell field test that we just conducted and provide a voice track here. This is the scene. We had on the order of about 40 buildings on this test site. We're deploying ultimately anywhere from 100 to 200 up to 240 robots to do this. Some of the enabling technologies includes this Hive. We call it the Hive XL, that can store, charge, and deploy drones from the rooftop and also recover them and reslot them. It's basically a robot that launches other robots, and it can house 80 drones here. We're showing some VTOL vertical takeoff platforms. Here are other fixed wing assets coming in, not just to do the typical overhead surveillance, but what if you can fly below ceiling height, below roof lines in an urban setting to do scanning and surveillance and other type of interdiction type tasks. And so again, the idea here is we have air, ground, mixture of types of air, etc. There's a web link there if you'd like to take another look at this video. But hopefully that paints a picture of the scale of the kind of operations that we were most interested in for the offset field tests. And so kind of stepping through the technology a little bit further, the main idea behind the offset program are these things called swarm tactics. And the swarm tactics really constitute this high-level representation of the capabilities afforded by the swarm that translate commanders' intents into morsels or bite-sized portions that the swarm or subswarms can go off and execute. And this is kind of in contrast to how we might otherwise develop from a bottom-up approach, where we technologists will develop algorithms, try to stitch them into primitives, kind of jam them into an architecture that allows that kind of stitching together. But alternatively, offset started more from the mission, like the minimum viable missions I described earlier, and defined what the types of plays or higher level ways in which you would break up a mission of urban complexity and try to develop from more of a top-down type of an approach. And I'll describe a little more of what I specifically mean. Just to highlight the way the program was structured, we had two teams. One was led by Northrop Grumman. You'll hear me refer to them as Team Rise. And the other team was led by Raytheon BBN, and that's Team CCAST. And we call these our swarm systems integrators for reasons I'll highlight in a moment. But these two teams were charged with developing the architecture, the virtual environments, the simulation kind of constructs, and then also the physical test beds to go and demonstrate all of these types of capabilities coming together. And the key takeaway for this audience is that both of these teams have developed repositories. We're using DI2E to house and develop and refine their code, but also the tutorials and the documentation, both for the user side and the developer side. And now we have these kind of fleshed out repositories of this swarm software. So kind of detailing a little bit more what we mean by swarm tactics, these repositories highlight, for example, in the upper portion of the slide, Team Rise's Swarm Tactics Exchange, that's what we call our repositories, highlights, and you see these phrases here representing kind of the functional behaviors or capabilities, plays, if you will, that swarms or subswarms can go off and execute. So that could be everything from follow a route to conduct a building scan, patrol a perimeter, maybe breach a building. These are the type of battle drills, if you will, that a swarm commander might use and stitch together as he or she constructs a mission plan. And then, of course, no plan survives first contact. And so, again, these are the building blocks by which she'd be able to, the swarm commander would be able to call audibles or restitch or reconstitute a new plan. Similarly, the lower diagram there shows, the listing shows Team CCAST's Swarm Tactics Exchange, and you'll see, of course, some analogs between the two. And in the circles, I'm highlighting this the different types of ways in which you could trigger or call these individual Swarm Tactics building blocks. So Team Rise elected to make use of a touch tablet with sketch gestures built upon a Unity 3D game-based environment. And so what you're seeing in the upper right circle are the sketch gestures that you would draw on a screen to instantiate and launch one or more of these types of tactics. And the idea here is it needs to be intuitive and quick to be able to interactively and immersively respond and interact with robots, the swarms. At the bottom left circle shows how Team CCAST went about developing their swarm interaction model, which is through, for example, in this case, virtual reality. Now you could be wearing a headset, have your virtual reality paddles, interact with a 3D sand table that you can float around or maneuver within. And these icons that you see, the glyphs on the left, correspond to your ability to tap those buttons to, again, instantiate or trigger the one or more of these swarm tactics listed in the purple below. And so let's make that a little bit more concrete. So here you should be able to see some videos, animations playing. In the upper two, that's with Team Rise using the sketch-based interface. And so you can imagine very easily looking in this interface, I'm drawing with my pen. I've outlined an area of interest in cyan. Maybe I've sketched a couple of red keep-out zones. And then I can just sketch this O-shaped gesture, and that triggers the overhead scan behavior that tasks available subswarm agents, into the subswarm, and that subswarm automatically and on its own self-organizes the overhead scan pattern. You can kind of see that represented in the upper right of that panel. They'll decompose the environment. They'll figure out who should be mapping which section, how to deconflict, and they do that all on their own. The swarm commander is only responsible for sketching in cyan and drawing that little O. And that kind of mimics at a slightly higher level. You can imagine a more complex level. You can imagine there are 3D buildings or other structures that you wish to scan. And I know that I want to scan the walls. So in the upper right, I'm showing the sketching of an outline of a building. And now I use a scribble spiral in type of a gesture. And that invokes a multi-agent inward scan. This, in this case, recognizes that we have 3D structure. It needs UAVs that have forward-facing cameras rather than downward-facing cameras. It'll automatically self-select agents from among that pool of downward or forward-facing cameras and deploy them and do that and do all of the collaboration necessary to be able to scan and rotate about the building, recognizing that they all want to point inward to be able to scan the walls. On the bottom, we have this virtual reality interfaces. You can kind of see the 3D sand table. This is collected from overhead imagery collected by a drone previously, turned into a photogrammetric 3D mesh, inserted into their virtual environment. And now you can do a very similar thing. You can specify geometries for surveilling areas, and it auto captures which agents are capable of doing that. Or you could use some semantics that you might have. You pre-labeled buildings or extracted information about buildings or intersections or key locations that you wish to target. That semantic representation can get selected with your virtual reality paddle. And again, by clicking on this one glyph, this button, it self-selects and organizes the appropriate agents, whether those be ground agents, scanning the walls from the exterior, or overhead agents being able to look down and do those types of collections. And so this is hopefully conveying how you would, per tactic, be able to do this kind of invocation. I'll highlight that typically when designing a mission, you'll highlight and stitch many of these tactics in sequence or in concurrent execution, and it'll be able to run the mission. But as I alluded to earlier, we know that no mission plan survives that first contact with the real world. And so the ability to autonomically define these types of tactics is an enabling capability. So to tease out a little bit more about these architectures, the general idea is to focus on the swarm tactics, recognizing that there are many underlying primitives or algorithms that the community has developed over the years and can continue to develop. And so really the takeaway message for offset swarm system architectures is the ability to take those contributions that might originate outside of the performers, outside Northrop or Raytheon internal, but rather from a broader array of different developers and researchers wanting to contribute. And so the takeaway here is that these architectures need to have that composability and flexibility, and to do so at the appropriate layers of autonomy, whether they all reside at the swarm tactics level or ultimately include some of the contributions at the primitives and algorithms levels. And so the program itself, the offset program, was structured in a way that would allow for, I'll call them third-party developers, to come in. We call them our swarm sprinters. And the general idea here is that the way I designed the program was to facilitate nearly every 6 months we were soliciting through a new BAA, new technology injects that swarm sprinters, these folks that were adding additional component technologies, they would be fed into and encouraged to integrate into one or both of these offset architectures for Team RISE or Team CCAST to contribute and enhance what is possible with these swarm systems. And so understanding how to do that across 5 total sprints, we've concluded our 5 sprints. We had 35 different sprinter efforts that spanned those 5 sprints. Each of these sprints were 6 to 9 months periods of performance. And that was aligned with getting a technology rapidly matured and integrated into, again, one or both of the swarm systems architectures and demonstrated potentially in the field alongside the integrator field demonstrations. And what you can see here is that some performers, whether they be universities or small businesses, or even large companies kind of working hand in hand to inject their novel technologies in at the appropriate levels. You see a couple of repeat performers who operated at different layers, universities contributing kind of latest and greatest from the literature, all the way to those that had methods or algorithms that they had used in other contexts that have been ported over to the offset context. And so this highlights the kind of existence proof, the feasibility proof of being able to integrate myriad technologies into the offset architectures, which was a core focus and design of the program from the get-go. So to highlight 3 such examples that we showcased just at the FX6 most recent technology demonstration, I showed clips of this earlier, but the fixed wing aircraft making use of hobby grade platforms and open source autopilot technologies, leveraging advanced controller design, but all resident on board. This is a foam aircraft now on the left panel there from Johns Hopkins APL, flying in corridors. They're able to scan buildings at the 1st, 2nd, 3rd story altitudes. There's an onboard camera that's doing all the collision avoidance and real-time calculation to be able to navigate in these urban canyons. And the rationale behind bringing fixed wing in, of course, is that the multi-rotors that we had been accustomed to were not capable of longer duration missions, nor could they be deployed from far away and infilled into the environment and then exfilled out. And so fixed wings in this manner can bring the benefits of multi-rotors, the agility that they bring, but also the advantages of fixed wing aircraft. Similarly, Sentient Robotics in the middle developed an 80-ship drone carrier transport charging capability. This is basically a 20-foot ISO container that you can haul in on the back of your truck or towed from your truck, I guess. And each one of these bays can house different types of drones. So it's just a matter of mating the type of drone to a particular bay. and robotically will kind of, you can just call for a drone, it'll get lifted up to the roof, will take off and join the rest of the fleet. And you can do this, it's an 11-second time between drone takeoff. There's also the ability to recover drones on the roof using visual indicators, those kind of 2D barcodes that you might have seen on the roof. And that allows for collection and recovery and recharging of drones such that over an extended period of time, you'd be able to sustain anywhere from 20 to 30 drones aloft persistently amidst the fully loaded 80 drone carrier. And on the right, I'm showing another method from Michigan Tech Research Institute. And the idea here is if there was this enabling capability to allow for spoofing and the ability to replicate or distract RED4 in key areas of interest, how would that be used to instigate or stimulate the red in a way that's favorable for blue? And so this is an example of how we were able to make use of both the simulation and the field test environment in one or both of the architectures, in this case, both architectures, to explore a future concept of enabling swarms to perform these types of spoofing type missions. And so that just highlights 3 out of the 35 types of initiatives that we were able to demonstrate throughout the life of the program. I alluded to it earlier. One of the key enablers, I think the robotics and autonomous systems community has definitely moved in a direction where we recognize the role of virtual environments in the development of advanced capabilities. And so our virtual environments, both teams designed and built virtual environments leveraging open source game-based game engines. So Team Rise in the upper part here is using Unity, Raytheon and Team CCAS using AirSim, which is based off of the Unreal Engine, game engine. And the takeaway here is that, of course, we're interested in leveraging the fidelity that these game rendering environments can offer us, but doing so with full physics and full sensor models and things really can impact the scalability of the simulator, where we're interested in testing and studying 200 or more robots operating at a time. And so to that end, we're of course interested in those large scales, but have to trade off the fidelity. And so both teams developed their kind of 3-tiered, multi-tiered, scalable swarm simulation capabilities, so that in the case where we do need to test at the kind of higher fidelity levels, perhaps as a pre-test workup or pre-mission rehearsal, if you will, for in-field test, they can go with a heavyweight or level 3 type simulator, or maybe make use of the lightweight level 2 scale simulator to be able to represent the kind of the physics level or the types of interactions that they might face. But if you're really trying to innovate or demonstrate different types of swarm tactics and design those swarm tactics at scale, then the featherweight or level 1 type of simulators really benefit that development and iteration. And so there were multiple instances where teams were, of course, designing those new swarm tactics. At FX6, for example, one of the teams, after conducting one of their experimentation runs, identified a potential behavior or set of tactics or composed tactics that would be advantageous. They were able to sketch that out, test it in simulation, and within a couple hours were able to provision all their robots again, and ahead of their next experimentation run had already gamed out, demonstrated, and tuned and deployed their swarm tactics to the fleet, ready for their next test. So that's exactly the model that we were interested in here. And so to that end, the offset program has developed both of these 2 environments that are now available for scalable swarm testing and development. And so this next chart shows you some snapshots of the simulator's capabilities as a function of that scalability I mentioned. You could do swarm mission scenario play in making use of those 3D models I alluded to earlier for having generated a photogrammetric mesh of a real test site. You could do things like seeing where sensors have seen over time. So that's the upper middle panel there, highlighting temporal coverage, and the magenta highlights what you've seen, and the fact that it returns means you haven't seen it in a while. So this is a tool that one can use to, again, game out and tune and design swarm tactics, and typically faster than real time. You can distribute the computation necessary, so put this on multiple hosts or even put this in the cloud to be able to do the higher fidelity testing across multiple computers or machines to be able to stress test some of the methods that require interactions with a higher fidelity simulated environment. The ability to do mission rehearsal, I already alluded to, the way that you can imagine deploying the software and running it ahead of an actual field experimentation run, incredibly powerful. And then the fact that you can interact with the environment both outdoor and indoor, really requiring a different sense of scale when you're interacting with these types of sim environments, is shown in the bottom right with the environment interactions inside a 3D mesh building. So hopefully that helps characterize some of the features, but also almost the required capabilities for addressing development in simulation environments. And I mentioned it earlier, but as a roboticist, we derive our street cred from deploying real robots in the real world. And so that was also the charge to these two teams to build and field physical swarm testbeds. And ultimately, the idea here was, what can we do with the baseline platforms available commercial off the shelf? The idea here is, if you could, for example, go to Best Buy or to other commercial vendors for these types of robotic platforms, what could you do if you enabled the ability to work as swarms? And the takeaway for this experience, I'd say, is that the commercial side and the consumer drone market, as you may well know, turns over very quickly. We've seen platforms become end of life and discontinued throughout the life of our program, requiring teams to go and find new suppliers, deal with supply chain questions, adopt new platforms, work with vendors closely to tailor the needs of swarm systems capabilities, vice maybe the consumer needs, and incorporate them quickly and demonstrate them in the field. And we've been able to do that across the board with the myriad platforms highlighted here. And so as part of that effort, being able to incorporate new hardware technologies has been part of the fun to learn what advances we can make, maybe leapfrogging or bootstrapping on existing platforms. So everything from the fixed wing aircraft that I highlighted earlier, from Johns Hopkins, that's the aerobatic maneuvering, whether that's below ceiling height or roofline height, to being able to do tail chasing. The university, Texas A&M, developing hybrid wheels that can operate nominally as wheels, but then can turn into legged mode for more rough terrain. And this is modeled off of the rovers that were used in the offset testbed. A couple of other platform enhancements that would have additional benefits to swarm technologies, whether that's instead of using RF to communicate swarm mate telemetry, are there ways to have onboard sensing as maybe applique kits, if you will, so omnidirectional cameras or maybe infrared beacons that would allow for me to know where my teammates are without needing to broadcast that using RF, as an example. And this all comes together with the way we conducted our field experimentation. So the government team, which was NIWC San Diego, was able to come in. We'll go to these different test sites here. I'm depicting our test site from FX4 as an example. We'll instrument the range, anywhere from 5 to upwards of 8 kilometers of Ethernet cable at our last field test that we laid out. Hundreds, we got up to nearly 1,200 April tags. These are the 2D barcodes that you're seeing in this picture. And these barcodes have a nested feature where the outer tag can be read at some standoff distance, and the inner tag can be read only upon getting a fair bit closer. And this represents kind of the way you would imagine ATR, automated target recognition, might occur. You can tell that it's a dismount, a human-shaped form from a distance, but it's not up until you get close enough to resolve whether or not that's a hostile or perhaps a non-combatant. And so we're able to exercise that element, for example, in this experimentation construct. And I know that there's a lot of machine vision or automated target recognition works happening elsewhere in the department. And so not wanting to hamstring ourselves and slow ourselves down, the idea here is to test and develop at the swarm levels of technology. And we were able to leapfrog, always keeping in mind the hooks to be able to incorporate those ATR type algorithms. And I'll speak a little bit more about how we've progressed that to date. And then, the ability to use these April tags now means that we have placed everything from representative hostile threats to non-combatants to benign objects to clutter, things that you would find in an urban setting that really take away from both the ability to resolve where threats might actually be, as well as overwhelm the human swarm commander. And we're trying to exercise that, including things like using, this is an e-ink screen, kind of like a Kindle screen, if you will, and you can remotely change this, and that would allow for the scenario to evolve throughout the experimentation effort. And all of this is all networked in to our government experimentation and orchestration system. We call it MOLE. And that system allows for us to do that orchestration and retrieve real-time interactions and metrics and such as the test is being conducted, let alone afterwards for post-mission analysis. And so from that perspective, all of these data that we're gathering from all of the Raspberry Pis that we've instrumented the field with April tags where the detections are being fed back, all of those are now fed into MOLE, the experimentation management suite of software. And what I'm showing you here are the types of coverage heat maps, or in the bottom right, these are our run reports that can document how quickly teams are deploying their agents, or what's the proportion between air and ground being deployed, how many buildings have been observed. These are the types of scenario-based mission-level metrics rather than robot or platform or specific component technology-based metrics. And we're able to generate these, and by the time the performer is done with their experimentation run, we've pressed print to PDF and emailed it to the team so that they can pour over it, of course, alongside any of the analysis that they want to do, and come back to the next experimentation run armed with the type of data that will inform how they should tune or tweak their deployment or employment of their swarms. So all of that working together has been absolutely critical for being able to accelerate how quickly we develop and advance this technology. Excuse me. And those run reports have been a key enabler that, again, the government has developed to make use more broadly to the community. I'll highlight one more element which speaks to the human swarm teaming aspect of the offset program. In particular, the idea that being able to speak, much like an orchestra conductor, doesn't tell each musician what note to play and when to play that note. We also want the swarm commander to more or less orchestrate, conduct this beautiful, symphony of execution of a swarm mission, and the richness that the swarm tactics affords. We're interested in having the interfaces also be able to leverage that richness as well. And as this program evolved, we had early on identified that it really depends what persona, where, what perspectives you're tasking these types of swarms or subswarms from that impact the types of swarm tactics one might develop. And so we identified 3 swarm persona that highlight both the command and control, or just really the command interface, as well as how the swarm interacts back with that human commander, whether you're kind of in a standoff distance, a standoff location as a mission planner. You could be maybe in a slightly protected location. This is near the battle, but not yet in the fight. That's the swarm tactician rear. But you could potentially be running around with drones and rovers flying and driving around you. And that swarm tactician forward has a different set of swarm tactics and different set of interfaces that would be most useful for him or her to manage and operate with the swarm. And so shown here are the virtual reality headsets, the sketch interface I alluded to earlier. We made use of HoloLens 2 or Magic Leap, but other augmented reality type technologies to be able to project where swarm elements were, as well as where mission plans were laid out in a scene. We've developed a tablet-based approach, including an ATAC plugin that, for those of you familiar, provide common situational awareness of where our swarm, blue swarm assets are located. And so all of those can be used in concert with one another to help scale and expand how we interact with these swarm systems as developed to date. And so the program has come to its technical program objectives and completion. We are continuing forward with an Army demonstration event. That's the Army Expeditionary Warrior Experiment conducted in March down at Fort Benning. And so we'll carry forward many of these technologies at the platoon and company levels to be demonstrated in that March timeframe. The idea there, I alluded to earlier, those hooks for automated target recognition. Having done that, we're able to pretty quickly import and make use of off-the-shelf trained classifiers like YOLO v3 in particular to be able to recognize things like vehicles and dismounts, and that's already enabled by the hooks, and we'll be deploying that and demonstrating that at AEWE here next month. So Offset has really created these repositories, this library, if you will, of collaborative autonomy software and the architecture that kind of bridges all of that. The two swarm virtual environments have demonstrated a bridge to the real world to a large extent. Of course, there's always room to improve how simulation is used and leveraged to bring together the real world. One addendum to that is the additional LVC, so the live virtual constructive type approach that was developed in Offset, so much so that in our FX6 field tests, we found that our swarm operators or swarm commanders sometimes not being able to tell which agents were virtual and which agents were real, and the fact that they were tasking agents kind of transparently highlighted that this technology of enabling scalability, even with the use of virtual assets in real life, was possible. And that's another way to leapfrog and advance how quickly we can develop these swarm technologies. And pertinent to this audience as well, there has been a pretty interesting opportunity to gather the types of data sets as well as experiences, the logs associated with this type of technology, everything from the terrain information, so the 3D mesh that we gathered with high precision, highly georectified, including things like scans of interior environments that can get, again, rectified into the virtual environment. All of our walkthroughs and so forth allow for maybe some semblance of replication of some of these types of experiments. And again, these virtual settings afford the scenario, so you can take the physical real-world scenario, load them into the virtual environment, and play back and play out what you might do again in the future. Some technology lessons learned, I'd say, having used and leveraged the baseline platforms. These are commercial, off-the-shelf, inexpensive platforms. I'd say we now have a firmer understanding of what an appropriate point of departure is. In other words, if I were to double the cost of a allowable cost per platform, anywhere from the 2,000, let's say, to the 5,000 or maybe the $10,000 range, here's the what is the impact on the swarm capabilities that you might be able to have. So 2x investment of cost might get you the 10x return on swarm capabilities. I think the question of why would you want to make use of swarms? Well, I think we learned that there are times and places where swarm tactics are better served for surging your forces. And that's where we call this a swarm power generation rate. You would want high or very fast swarm power generation. And there are certain swarm tactics that benefit from such surges or amassing of your swarm force. But there are other applications or other swarm tactics or other components of missions where sustaining the swarm power over longer durations of time are more advantageous, such as surveillance or tracking type tasks. And so now we have that better understanding of how to design and apportion and allocate subswarms for surging and subswarms for sustaining elements of the swarm mission. As I hinted at the very beginning of the talk, we're just covering down on the swarm autonomy and the human swarm teaming elements. There's a whole slew of other technology areas that I certainly think warrant further investment and investigation. Everything from really understanding the needs of the urban environment for urban maneuver capable platforms. I think using our four-wheeled rovers highlighted some of those limitations, and I think being able to invest in advanced robotic platform capabilities will really allow us to leapfrog to the next plateau of capabilities. Swarm logistics, through and through, one of the hardest pieces here, but understanding what it means, kind of armed with the knowledge that some tactics require surging. So how do you do mass launch and or mass replenishment, coupled with the sustained approaches where you can sequentially launch and sustain flight ops. I think there's a lot of opportunities there to design and develop new technologies. And then at the end of all of this, of course, we're advancing Blue, but I think it has given us a lot of insight into what it means to potentially defend and counter against such advanced technologies as well. And so I think there are great, rich opportunities to further go down that route as well. And so that brings me to the end of this talk. Really pleased to have had the opportunity to share the offset program with this community. There are many other programs at DARPA that continue to try to advance innovations of autonomous systems in complex environments, and happy to either identify other areas or forward interests to appropriate folks of my colleagues at DARPA. And with that, thank you very much to the audience today. Happy to turn it back over to Brian.
Yeah, thank you, Dr. Chung. That was a great presentation. We did have a couple, one question that came in, but I do want to remind everybody about the question and answer kind of forum here, portal you can enter. Just kind of click the top middle of your screen, type in your question, and we'll fire them over. So got two of them in queue actually right now, so you'll be able to get the ball rolling. So if you're ready, Dr. Chung, first one that you could see on the screen, but I'll just reread it for those who are just simply dialed in. The question says, can you talk more about what RF-free tactics you explored? It seems to me that one of the largest challenges to swarming is that it typically relies heavily on drone-to-drone and drone-to-operator communication, but the future battlefield will probably be a highly contested EM environment.
Yeah, thanks, Nicholas, for this question. First off, I'll say that I think that swarm networking, which is one of those pie wedges I showed earlier, that absolutely can be its own program and longstanding investment, I'm sure, because you're hitting on exactly one of those key areas that I think absolutely needs to be explored. So to kind of flesh out the context, Team Rise, one of the teams ended up using a commercial mesh radio, so a meshing radio that operated in 2.4 and 5.8. And in those settings, they were meshing and communicating amongst each other and back down to the command station. And then the other team elected to use tactical LTE. So now they're using a USB LTE modem that's affixed to each of their platforms. They are talking to a LTE base station. The way in which all the coordination happened between all the swarm agents was agnostic to the fact that the comms was being piped through a base station. It was as though they were talking to each other. But you're absolutely right that both are highly dependent on availability of RF in future environments. Now, the types of things that we did develop that we're trying to leverage RF-free approaches include things like being able to observe the environment and navigate relative to the environment. So those are just from a path planning and trajectory generation type of an approach. There were those types of underlying swarm primitives that were pretty commonly used. that includes collision avoidance and other things at that level. There were other kind of open loop, if you will, so non-RF based maneuvers that were designed to be able to just go, especially if you become disconnected, how can you still conduct the mission? So that included kind of predefining locker room agreements as you're deploying a tactic. Hey, you guys go off and do this. If you happen to lose comms, just proceed as originally planned. If you don't resume comms, then come back and get and stand ready for retasking. So there were kind of almost like the intermittent comms and the comms loss type tactics that were developed, so that one could potentially operate if comms went down. But I totally agree that there are all sorts of additional technologies. I also hinted that the some of the hardware-based developments, like the IR beaconing, imagine kind of a lighthouse tower on board every robot, kind of alerting its neighbors with his beacon, but just like your remote control for your TV sends out encoded IR blips, if you could do that to pass messages or at least do identification of friendly swarm mates, that would be one way to alleviate the need for specifically wireless RF being transmitted. So those are some of the places where we played, but would love, and perhaps that's an opportunity for this community here to highlight potential future programs at DARPA or elsewhere that could benefit from studying highly contested settings. Thanks for the question.
Yeah, that was a good question. Good way to kick it off. We do have some more that came in, so let's move along here. Next one is asking, what 3D scanning technologies were employed to collect the interior 3D meshes that you showed?
Yeah, thanks, Chris. So this was honestly just using a free iPad app. So there's a 3D scanning app using the iPad Pros, and we literally went around and scanned the buildings with a pair of iPads to be able to generate those meshes. So nothing particularly fancy. I'd say your mileage may vary depending on. We did have troubles with the unlit rooms and so forth, but opportunities there to do that.
Gotcha. Okay. All right. Next question is, to what degree is the embedded code and control elements protected from adversary discovery in operations?
Okay. So first off, I'll say that we did not explicitly protect or aim to defend against this type of an attack surface, although we certainly recognize that in operational settings that we would need to worry about all of these types of considerations. I'll say also that much of what we developed is openly available. So the code base for the flight controllers, that's all based off of either Pixoc or Autopilot, which are openly available open source autopilot flight control software. Built upon that, leveraging open source middleware, namely Robot Operating System, as largely the core for both of the software architectures, again, which is an open source capability that's readily available. And then, of course, there were considerations for things like ITAR protections, but by and large, most of the code base is openly available, apart from some of the protections for ITAR considerations. So if you were interested, you'd be able to go and download and launch the virtual environments today and make use of it. The robot stacks, again, with the caveats for ITAR, are also potentially available on DI2, or are available on DI2E, so that you can make use of it. As far as in-field during operations, there's very little protection for the platforms. Again, this is an R&D effort, not specifically focused on securing that element, but absolutely recognize that is something that needs to be incorporated. Thanks for the question, Michael.
Yeah, it's great. And actually, just quick follow-up. You mentioned DI2E. That is the library that you referenced for collaborative autonomy software and data that was used for this?
Yeah, that's right, Brian. So DI2E is a service, I'll say, that is provided. It enables CAC enabled access, which was great for us to be able to kind of do a little bit of access control, but also facilitate openness. It services both a Confluence wiki for documentation, but also the Bitbucket software, version control system for code development, and a variety of other things like Jira tasking and such. So Di2E is kind of the umbrella that is government provided, DoD developed and provided, that provide a really great set of tools for those of your audience that aren't familiar. We used it to great effect for the offset program.
Good. Yeah, I just want to make sure to highlight that. Okay. Next question. Could you please comment on the high-level mission objectives that were emphasized in the program?
Yeah, Brad, thanks for the question. And I realize that maybe I should have let out a little bit more on that topic, but in particular, the scenarios that we were investigating, stemming and building on things like isolating urban objectives, conducting urban raid, and seizing urban terrain, were focused on this scenario where there were one or more high-value targets, individuals, somewhere in the urban environment, and that spanned anywhere from 10 to 40 buildings, depending on the field test. And so the objective here amidst, so we've secured a foothold, let's say using the last experiment as a case study, we secured a foothold to the south of the urban enclave. We knew we were going to proceed into this environment. We knew that there were high value targets and that hostile threats. So Red had kind of hunkered down and placed remote IEDs or put up sentry turrets, or there were dismounts with simulated small arms, with small arms that we were simulating. And so the idea here is, 600 hostile threats in this environment in one fashion or another. And so now we're deploying these hundreds of robots to conduct that original intelligence and reconnaissance of the ISR mission, trying to find where there were hostiles or where there were benign objects that we didn't have to worry about, trying to keep awareness of that. But then as these intel queues were popping up, we would want to redirect the swarm or the subswarms to go and interrogate specific buildings from the exterior, potentially ingress in to find where these simulated high-value targets were located, chase them around if absolutely necessary. So those were kind of the high-level mission objectives, in that locate the high-value target, do it as expediently as possible. And then kind of secondary to that were things like cover as much of the area as possible, reduce attrition as much as possible, but guaranteed every experiment run had, both real due to collisions or something, but also, simulated surrogate attritions incorporated as well. And so how the swarm commander was able to adaptively combat the dynamic scenario, that was really what we were interested in here. Hope that answers your question, Brad.
I think it did. Thank you very much, Dr. Chung. Well, and time-wise, we were right on the button here. That was the end of the Q&A, and the questions that came into us. I would encourage, if anyone does have any other questions, that you can either send them our way at DSIAC.org. We'll help answer some technical questions you might have, or I'm sure Dr. Chung would be happy to field some questions directed to him later on. But in the meantime, I do want to say thank you, of course, Dr. Chung, for your time and the presentation, and for everybody else for joining in. I think it has been a very valuable presentation, and great to have everyone participate in this.
Yeah, absolutely. Thank you so much, everyone. It's been a pleasure to participate, and welcome engagement from the community.
Very good. All right. Well, thank you, everybody. Have a good rest of your day.